So is everybody excited for today? Yes? So this is a very important lecture. I know I've said important lecture many times.
Aren't they all important?
But this is very important. I mean, just like there are Los Alamos people listening in, every university partnership is important for Los Alamos. But Michigan is very important. So that kind of lecture. All right. Okay. So today we're gonna be we'll be deeper into the ideas that we discussed last time, and I think you've seen this drill a few times already in this class. Some very important things we cover twice, right? We get a run through and then we jump in with more detail. Okay, so that's the goal, and we'll be doing this operator viewpoint. Let's call it, let's give every lecture a name. So today we'll call it a very fine view, which is looking at operators in a bit more detail. And I'm sure you have many questions from last time, because for many of you this was the first time you've been exposed to any of these things, and I threw 4 operators at you, I threw semi-groups at you, and a bunch of things. But today we'll go through them much more carefully. So before that, I want to see what are some of the questions germinating in your mind. So is there anything particular that's not sitting here? Go ahead.
Can you give a formal definition of an adjoint?
Okay, we'll do that today. So we'll actually derive equivalencies. Anything else?
Just because you mentioned semi-group right now,
Yeah.
could you just give a quick idea of what the semi-group formulation entails? Because I think that's not easy.
Okay, good. Maybe that's a good starting point for us. In fact, okay, so let's start with semi-groups. And it's really the notation that I think confuses a few people if you're seeing it for the very first time. And before that, let's start with something that everybody knows how it works, right? So we saw this last time. If you have just a linear ordinary differential equation in n dimensions, then we know that we can write x at any time as z is e to the TL c, right? So this is precise. There is a precise definition of the matrix exponential. It's a linear ordinary differential equation, so everything is clear, right? So let's go step by step. Anybody in the class not comfortable with this? Okay, good. So now let's take dx by dt equal to f of x, okay, and x at 0 equal to z, right? So let's take this now a more general nonlinear ordinary differential equation. And what we have to define is a flow map. So to define a flow map, let's call it phi t of z, right? What does a flow map do? A flow map takes any initial condition or a state at any time forward. Okay, so that's what it does. So you basically go from, I'm just writing it loosely, you go from z to x of t. Okay, so that's what the flow map does. Okay, of z. And similarly, if you take the flow map, but if you take the state at any time, right, you have some x of s, and you apply the flow map to it. You have x of x, you basically get, sorry. So this is x of s plus t. Okay, so this is the flow map. It's basically effectively moving the solution forward, right? It's the solution map of the ordinary differential equation. Yes.
For linear systems, is a state transition matrix basically that flow map?
Yeah, pretty much. The application of the flow map is basically multiplying that by, yeah, it's just a linear transformation.
This is just one more general.
This is more general. Okay, so let's start boxing things. Well, we know what a matrix exponential is. And we know what a flow map is. And again, semigroups, if you look at the notes, continuous semigroups have a bunch of properties. You know, if you apply the flow map at time t equal to 0 to itself, you basically get identity and things like that. But the important property is, you know, there is a connection between, so now, okay, so we know matrix exponential and we know flow map. So let's now define a generator, okay? So this is where the idea of a semigroup comes in. So if you have a semigroup, I want to think of this as a semigroup operator. I'm going to give you the connection between that and the generator, okay? So now let's, the generator of a semigroup is defined as the generator. I'm going to call the generator as L. And now this is the definition. Now we'll be precise. So limit t tends to 0, 0 plus, let's say. Cannot be negative. So you have a flow map. I don't want to confuse people. I'll just say X. So I'll just say G. Okay, so now this is the definition of a generator. So in the linear case, this generator L would basically be the definition of the exponential, okay? It's the same thing, but in this case, if you have, so this is a flow map is a semigroup, okay? So, and the connection between the generator of that semigroup and the flow map is given in this form, okay? So if you do it in this form, then, so again, if you say e to the TL, let's say x of s, then you can, so this is basically x of s plus t, because this is an equivalence you can write. Again, so the notation is a little bit sloppy because, you know, again, I think there was a question in the last lecture. Oh, but you apply these to scalars. Okay, so we apply this to every component of that vector. Okay, so then that's how it works. So this is the definition of a generator. Of a semigroup. Okay, so we've defined matrix exponential, which you know from before. Then a flow map takes basically it moves the solution forward in time, and then we have a generator. Okay. Any questions on this? So this flow map is the fundamental quantity from which everything else is derived, and you can see why, right? If you know the solution of the ordinary differential equation, then everything else, any operator can be derived from it. So in the same sense, yeah.
That psi is the map, right?
Yeah, this phi is the flow map, yeah.
And then what does it has to do with the semi-group?
This is a semigroup.
So
This is an element of a semigroup. It's in a semigroup. Let's say it's a semigroup operator.
It's an element of a semi-group.
Sorry?
It's an element.
Yeah, you can think of that way, yes. So you can think of it as parametrized by T. This is how you think about it. The exact definition is in the note. There are a few properties that need to be satisfied. To be very precise, you need a function space, you need continuity and other things. That technical detail is in the notes. But I want to make sure you get this. But I want to, before we jump to the next thing, I want to mention, yeah, go ahead.
I just want to get a better idea of the structure of
Yeah.
each element. So I is a set as an operator.
Yeah, L is, phi is also an operator, right? Like so which way how should I describe this without? So you apply phi to any point in your domain. It basically advances that forward. And if you think of it as a set, then the output is a set. Okay.
In that
Yeah.
case, then the flow map would contain the dynamics of the system.
Oh yeah, the flow map is
It's-
effectively the solution operator. That's what it is. It contains everything. We never, in reality, unless you have very simple problems, you never see it explicitly, right? But there are ways to, but of course, if you actually solve the PD, so the differential equation numerically, and you have enough samples, then you can basically construct an approximation. Okay, so now we want to, so what is the flow map in the stochastic case? Okay, so that's very important because that's the context in which we're going to see the four operators. In stochastic ODE. So again, you have dxt, let's take scalar for now, b of xt dt plus sigma of xt dwt. Okay, so this is the stochastic ODE. So now here the flow map is so earlier the flow map would basically act on x. Okay. But here the flow map is stochastic. Okay. Because there is stochasticity here. But what I want you to take is, so this is a deterministic map, okay? So for a given sample, the map is deterministic, right? So you have some initial condition in your stochastic ODE, and then you move it forward, it generates many realizations, okay? So that, for a given point in sample space, this map is deterministic, right? But then if you want expectations, then you basically take an expectation over those samples. I want you to think about it a bit and ask me some more questions. So for each fixed omega, right? Omega is your sample space, right? Sampling comes here. Well, if this doesn't exist, then there is no. Then the flow map is deterministic. But I'm saying, if you fix your sample in your sample space, this flow mapping operator is also a deterministic map. Okay, so is that is that clear? So there are two things that are fundamental. So again, right? So we're going to see four of those operators: the Koopman operator, Perron-Frobenius. We'll see the Fokker Planck equation. We'll see the backward Kolmogorov equation. But for all of those, the fundamental quantity is this. Well, there's a T here. The fundamental quantity is this, and that should be obvious, right? If you know the solution map of any equation you're solving, everything else can be derived from it, right? But this is fundamental. Now, there is something also fundamental, but less fundamental than this. Okay, I'm going to write this joint density function. So this is, again, I want you to think. Okay, now I pose a question, right? So what does this mean? Okay, somebody tell me what this probability means.
Given we have our initial, assuming position or state or whatever omega we had fixed.
Right.
If we advance in time,
Yeah.
probability that our
This is initial state, initial time, and think of it as advanced state. This is advanced time. So this is the joint PDF, and we've seen many times already, right? You get the joint PDF, then you pretty much solve the problem. But the flow map is a little more fundamental. Now, this requires a little bit of imagination, but we can derive it very precisely. How would you write the joint PDF in terms of the flow map? So this is a question for all of you. I'll give you 2 minutes to discuss. I did not put it in the notes. I'll do that today. How can we write?
And then we define it. Quindi come una peritoral integrale.
It's a question.
No, actually,
I don't want to single out the Gordievsky group, but yeah, you guys live in joint PDF land. You're excused.
Okay.
You're just entering joint PDF land.
So if I
Next
got
year.
the PDF from
So how would you write this?
there we go.
Is it true that one object here is deterministic and not the other one?
Yeah, this this map is a deterministic map, okay? For a given point in your sample space,
Okay.
your trajectory is unique,
In that sense.
right? Right, and remember in the last class I showed you a bunch of realizations.
The condition is
Right.
the
For that one particular sample, that is unique, so that map is unique. If you keep hitting the same sequence of samples, you're gonna get exactly the same thing.
So it's a kind of a rate of change. You will divide it by something. Exactly, that's what makes it marginalization.
All right, any thoughts?
So like integral phi tx d omega.
Integral phi tx.
Over all omegas. And then by some normalization.
Correct. Yes. Actually, that's very intuitive. So, first of all, so what are we? So think about what is happening, right? So there are many. So this one is a deterministic map. Okay. So for a given omega, there is only one way the solution will evolve. Okay. But I think this is what Amal is trying to get to. Is there only one way to get from x to y? No, right? There are many different ways in which you can get from x to y. So you have to do some kind, so you've actually lost some information here if you think about it. And that information is what he's saying, it's an expectation over omega, okay? If I want to write it precisely, I want to write something like this. I want to write delta of y minus phi t of
How these just
x comma omega, okay? So there are, many possible paths, right, that if flow map can take a given state to, depending on the omega. So this one, for a given omega, this one is the unique path. And if I take expectation over all omegas, then I basically have what I need. Okay, so P of y comma t given x comma 0 equals. So again, so this is effectively one particular. So if you pick one particular omega, you're going to get this y. Okay, and you're picking out that particular y. But then there are many possible y's that can be reached because omega is changing. So this is how you write your joint PDF. Yeah.
Is this the push forward?
Yeah, we will define that push forward. Yeah, I mean this is push forward in a certain sense, but today in the context of operators, push forward means something very specific, the Perron-Frobenius operator. Okay, so but yeah, it's the same idea. Yeah.
So just for clarity, the flow map that we defined for the stochastic ODE, the omega in it is the trajectory.
Omega is
Sample of
sample
trajectory.
space. Yeah. So just like every random way. Okay. Actually, there's a very important point you just mentioned. You brought up. Phi t of x comma omega is not a random variable. It's just a deterministic thing. Okay. But x, when I say xt, that is a random variable, right? Because of this.
Okay.
But phi is deterministic because you do like a bookkeeping, no, of omega.
Yeah, exactly.
Yeah.
So let's go to your digital computer, and let's say you had infinite precision of computation, and you initialize a seed. You say the seed that you introduce, and you keep track of all of the seeds. Then that's the bookkeeping. So I've said many times in this class that the joint probability is the fundamental thing, but the joint probability is like a mesoscopic view. This is the microscopic view. Even here there is a microscopic view and a mesoscopic view. Microscopic view, you bookkeep every possible thing. You record everything. Actually, there's a very nice entity connection, the Maxwell's daemon, which also comes down to like this bookkeeping thing. But anyway, yeah. So I want to make sure everybody's on board. Yeah.
Why do you use the lowercase delta there? Is that a Dirac function or
This is the
not?
Dirac delta. Yeah. This
Okay.
just says. So remember, this expectation of omega means it's an integral, right? I'm doing an integral over all costs. So this is what I'm always saying. So integral of this delta of y minus dt x comma w over all possible omegas. So anyway, I don't want to squeeze something there. Yeah, it is the Dirac delta function. It basically picks out those particular values of y. And then you average over all of those y's. That gives you the joint distribution. Okay. Okay, good. So now we have, what have we seen so far? We've seen, well, the metric exponential. We've seen flow map. We've seen the generator of a semigroup. And then we've seen this. So that's all that's needed to now very precisely define the four operators that we briefly saw in the last lecture. Okay, any other questions? Okay, so where can we jump right into the operators? I think we can. Okay. All right, so let's start with the, I want to make sure we start in the right place. Okay, so let's start with the Fokker Planck equation. So now we do the big four, right? Write it down. So first is Fokker Planck. Again, everything is for this stochastic ODE, okay? So for now we will be scalar domain. In the notes you also have the vector. So for now just everything is a scalar. So everything we'll write is going to be connected to this scalar stochastic ordinary differential equation. Okay. So now let's say you have a probability density now. Probability density of x comma t. Okay. So this just, so if your initial condition is basically 1 point, then rho of x comma 0 is just a delta function, right? So a Fokker Planck equation basically it moves forward the density. Just like we move for the flow map, move forward the state. The Fokker Planck equation moves forward the density of the states. And the operator that moves, so Fokker Planck is an equation, okay? And the particular operation that moves it forward is called the Perron-Frobenius operator, okay? So, but let's write the Fokker Planck equation. It is d rho by dt equal to minus d by dx of rho, b is a function of x, plus b squared by dx squared d rho. And we define this right hand side as L star rho. Okay, so again, it's the same stochastic ODE, but we've defined a new quantity here. This is half sigma. So if you forget this, it's very definite. You know what a probability density function is, and you have some equation that governs the probability density function. And this whole operator acting on rho, I call it as L star. But L star is the generator of this semigroup, which we call as, so closely related thing. I'll explain to you why we have a star. And then you have a Perron-Frobenius operator. And the Perron-Frobenius operator, if you use the semigroup notation, okay. So d rho by dt equal to L star rho, then e to the t L star applied to rho basically moves rho forward by time t. Okay, so this is the definition of the Perron-Frobenius operator. But again, the difference between the last lecture and this lecture is we will connect everything concretely to objects that you know well. And you know, I mean, you understand what a flow map is, right? Basically, it is the solution operator for that differential equation. And we related the flow map to the joint. So if you want a precise definition of PT, then okay, let's apply PT to something. So if you apply this PT to some rho naught, and of course, everything is a function of x, then this would be, okay, I'm asking you now, again, second question. How would you write this in terms of this joint probability? Given we've already defined things before, this would be an equality.
Would just be ETL star times rho?
Correct. So that is, yeah, e to the t L star times rho naught. That's correct. But I want to write this in terms of the joint probability distribution, because all of us understand the joint probability distribution, right? Which is what we've been working with. What would this be in terms of the joint PDF, joint probability? That in terms of this quantity here. Let me write it. So we're going to have, first of all, it is operating on rho naught, right? So that's going to be there. This is going to be P of x comma t given y comma 0 dy. Okay, so this is now a very concrete definition of the action of the Perron-Frobenius operator on density. And what does it do? It moves things forward, okay?
Could you redefine y, please?
Y is basically, okay. So y and x are basically representing the same object, but you just, if you basically integrate this, you get x. So I could have used y here, then I could have used y here and x here, but x is basically our state, our space, right? So effectively what we're doing is, so if you're saying, okay, I want to go to the initial density, okay? And I'm interested in the density at some time, okay? And this is equal to rho of x comma t, okay? So I want to go from initial density to final density. And I know this joint. So what is a better name for this thing? Forget this class. What would you call something like that? Sorry? What happens when you integrate joint distribution? What? You're marginalizing, right? So it's like you're taking all possible y's.
What is y?
What is x? Let me get, what is x?
X is the state vector
X is the state vector. Y is also the state vector.
at some later time.
In this particular case, at the initial time.
So it's the initial state.
Yeah.
Is that not z?
Well, z was in the, no, I'm glad you're connecting everything we've seen. We did not introduce z in this problem. We placed the role of z in the scalar ODE. But I'm glad you asked, right? I'm sure there are like 10 people in class who had the same question but didn't ask. Or maybe 20. Okay? So, or maybe
y.
what?
Number of people in the class.
Yeah, so anyway, so point is, this is the initial density, and this is the density at time t. And they're basically related via this. Because again, as I've said many times, if you have the joint distribution, this is basically the transition probability, right? It's the probability of transitioning from y to x in time t. So if you integrate all of those weighted by the density, then yeah. So if this was uniform, then all of these things have the same likelihood of ending up at the same place. So anyway, yeah, I'm glad we're asking questions at this level. And now,
Just to clarify, so the Perron-Frobenius operator takes us from the initial to the
final
density.
Yeah.
What does the Fokker Planck operator do? It
If you-
represents.
Yeah, it's a generator,
Okay.
right? That's the thing. So L star generates P. L star generates PT. Right? So just like you had your, in the previous case that I showed, you have your differential equation that generates the flow map. It's the same idea. Right? And remember, L star operates on density. Okay. So let's very quickly see. I mean, we saw this last time, we'll see it again. So we take a very simple, not necessarily very simple, we take this particular stochastic ODE, right, this one. Drift is x minus x cubed, diffusion is, or sigma is 1 over whatever. And so the Fokker Planck equation for this, sorry, this should be a sigma. Okay, so the Fokker Planck equation is this. And yeah, this is what happens. So again, this is the evolution. Initially, we have a delta function, okay? I think that's probably also mentioned in the problem. Yeah, so all of the states start at x naught equal to 1, which means the rho naught of y is a delta function. So it starts off as a delta function. You apply the Perron-Frobenius operator to it. It becomes Perron-Frobenius operator parameterized by t equal to 0.5 to it, you get this, right? And then it evolves. That's the equivalent of solving the Fokker Planck equation, which is the generator of the Perron-Frobenius. The reason why we spend a lot of time is once you have these operators at hand, then a lot of manipulation becomes easier because everything, again, I forgot this, I mean, I mentioned it last time, I forgot to emphasize it, and I even forgot to mention it this time. The beauty of all of this is, even if the underlying dynamics is nonlinear, underlying dynamics is stochastic, the operators are all linear operators. Okay, so then with linear operators, we can do a lot of interesting things. Okay, so this is the Perron-Frobenius operator. And now, so there is a duality that we will now take advantage of. Because so far we've operated directly on densities, but it's not, sometimes it's not all about densities. We're also interested in operating over functions. We're interested in tracking expectations, which is where the, and by the way, this is called Fokker Planck. It is also called the forward Kolmogorov equation. It's the same thing. And by the way, I've been playing with the latest AI models like Claude Opus 4.6 Pro, all the best versions. And if you don't know what to ask, how to ask, it can give very confusing responses. And I don't think, and the models at this point, they know everything, it seems like, but it can be very confusing, especially when it comes to backward Kolmogorov. Okay, so we're clear on this, right? So now let's do the backward. The name backward itself can be super confusing for a couple of reasons. But we'll also see that there are two different ways of looking at the backward Kolmogorov. Okay, there's a forward interpretation of the backward also. So let's look at the backward Kolmogorov. Again, just like in the case of the Fokker Planck, there is a PDE, and then there is an operator corresponding to that PDE, right? The operator that generates this. So the backward Kolmogorov equation is given by backward Kolmogorov PDE. Before that, just like here we defined, it operates on the density of states. This one operates on U of x comma t. So this is a little bit more involved, but you get that. So this is the function that it describes. So now we've introduced a few more things. Okay, the first thing we've introduced is we don't have the state anymore. We have scalar functions of state. Okay, well here everything is a scalar, but even if this was a vector, we're still looking at scalar functions of the state. And then we have a conditional expectation. I made a mistake. And this is where most of the confusion comes. It is a scalar function of the final state. And then I'm taking a conditional expectation with respect to a particular time, and t has to be less than or equal to t. Yeah, think about it for a second and tell me if that makes sense. And for you, there's a very good example I can give related to Wall Street. Right, so it is called backward because we are saying, so you're saying I am at a particular state now. So again, think of, okay, let's think of time. Time is in this axis, let's say. And let's say x is in this axis. And you have many realizations. Now you're saying, and let's say this is, okay, so this is time, sorry. And this is a particular time. So if you're at any given time and you're at any given x, u tells me, so I'm already here. Tell me what is the expectation that I end up at this time. Okay, that's what it means. Given where I am now, what can I expect at time t? Okay, so remember, you think of it as trajectories, or think of wherever you are. Okay, you are at a particular point you're at a particular point of time. You have a particular, say, you're at a particular point, and you're asking, where do I expect myself to be? Okay, and in other words. And where it comes from is, well, there are different places where it comes from. I think one of the interpretation, comes from a Wall Street type thing. So I have a particular payoff at time t, but of course, if I did everything perfectly, I would get that. If everything was completely deterministic, I would get that payoff. But I made whatever choices I've made in life, and I'm here. Given I am here, what payoff can I expect? Okay, so, and that particular case is the Black-Scholes differential equation. Basically describes that dynamics. The backward Kolmogorov for that particular application is called the Black-Scholes equation. Okay, but anyway, that's just a detail right now. But so again, it is backward because you're asking, I'm here, what do you expect? What can I expect at time t? So everything is connected to that capital T.
But shouldn't then u be a function of capital T?
Yes, you could maybe say something like this, yeah. You could say something like that. But it's kind of implicit. And yeah.
Is there a reason why we condition the Perron-Frobenius with respect to time 0, and here we say pick the state at any time?
It's whether you're going forwards or whether you're going backwards. That's why. That's why it's called the backward. It is with respect to some time. But, and I think the reason why people get confused is you can change the sign of time, and this also goes forward, and it's incredibly useful for us also. So But yeah, we'll get there. But I want you to, okay, I just want to say one thing and I'll give you some time to think, okay? So, and this, oh, I did not write this equation, okay? So this is du by, the backward Kolmogorov equation is this. d du by dx plus d squared du by dx squared equal to 0. Or and then you need a final condition, right? So this is the backward Kolmogorov equation. So everything is described here. Remember, for the forward Kolmogorov, you needed the initial density. And for the backward Kolmogorov, you need the final function. I'll tell you that this can, by just reversing time, you can also move forward, and that's very useful in a lot of problems. But going backward is also useful, especially in control problems. If you're trying to achieve a goal, or you want to go towards something that, basically, I've said enough, right? If the goal is control of some sort, you solve this backward. But in many cases, going forward also helps in this setting. But you're solving here for conditional expectations and not for densities or functions. And what you saw, the Liouville equation that we saw in the beginning of the previous lecture, is just the deterministic part of this. Okay, so the only thing I want to write, and then we can take a break, is the Koopman operator. And this is written typically as du by dt plus lu equal to 0. Okay, this is how it's written, where L is given by this operator here. And the Koopman operator, now, the last one. The Koopman operator is basically generated by the backward Kolmogorov. So kt, but Koopman operator operates only on functions. Can also be written in terms of the joint PDF, which is just the interesting part, but I'll just make an expectation in terms of a joint PDF. I'll just leave it there. So the Koopman operator is generated by the backward Kolmogorov operator L. Okay, so let's take a short break, 4 minutes. Break and then we'll come back. Yeah.
Options pricing?
It's used in many contexts, but primarily for options, I think.
US actually.
And usually options, sorry.
US options.
Okay, I see.
Because in Europe they have a different.
What is that called?
The Black-Scholes model was done for only the US.
What is the European? It's called European options, actually. So in the Black-Scholes,
Specific probability in that value given. Okay.
D at time t.
Okay. Versus the function.
Time stepping schemes of Liouville.
I need to go to a solution.
Looks something like this.
Yeah.
They're of Liouville, right?
They are.
Okay. Why am I like mixing ordinals functions?
That's why time stepping is.
You want to achieve that. You are in a particular time. What is the expected value that you get is what it is.
because this theory assumes that
Like where are you
everything
gonna
is Gaussian.
find the like where? Yeah.
Then it forces you to discretize everything so that you have a time step and a time and a special discretization so fine that it is actually Gaussian.
Right.
But
Yeah.
there is like a kind of
Yeah.
it's like kind of forgetting things. It's like
Yeah.
imagine
You're
you
losing it for that.
imagine you have a girlfriend. And
Yes,
you,
yes, I'm on
you don't
the.
really want to understand your girlfriend. You just want to know what she's doing.
Yeah.
You're a really controlling
Yeah.
boyfriend. So you are calling all the time. What are you up to? What are you up to? What are you up to?
Yeah.
And because you call her every millisecond, you know what she's doing. But if you actually hold a memory and you understood what are the dynamics and the forces that drive your girlfriend, you will need to call her constantly.
Right.
You will need to call her in the
Have them all on
morning,
and
tell her
Yeah.
how you will sleep.
Grab them.
You will need to be worried because trust.
Those don't.
It's not
And I
based
bet
on
these are
something.
erasable.
Trust is not memory.
Even though they're not less, but
But
Yeah.
all fluid community is based on
this is my
trust
zero
from
one.
humans. And trust
Yeah.
from people that they want to sample faster,
Yeah.
finer. And what is the limit? In Reynolds to infinity?
Because the density, yeah.
Low Reynolds.
It's because we have too much uncertainty in each step, so we like make it fine.
But the
Yeah,
higher the
yeah, yeah.
Reynolds, certainly will explode.
Yeah.
So either you have an assertive principle
Yeah.
or you're fucked. And this is what I'm trying to propose with these travelers around the sphere that I said. I said, and this is a beautiful example. One guy, you're an observer in the equator.
Yeah.
And one guy goes in a straight geodesic from North Pole to the equator. And the guy goes on a spiral.
I understand. I guess I looked at it 5 minutes, but
With everything you have, with that, then you say one particle, then you say a density, and then you have a cloud, and the cloud is
Okay. Yeah.
and then you say, okay, with coarse information, infer the trajectory of the cloud. You need uncertainty.
Right. Yeah.
And the uncertainty becomes the local ellipse of the cloud. So in a cloud, we're in the sphere. And let's say now we are in a cloud, and I only have kind of a coarse representation of your system.
Yeah.
I don't have every point. But then I ask you, what if we basically do
these are all
a system that takes this?
Okay.
So what I'm tracking is I'm tracking your position, and instead of asking you every time,
Yeah.
what I do is I track here,
Yeah. I don't know if I was gonna go.
here, and your hemisphere.
Yeah.
And I say that this gives me the same information if I sample over time.
Get an idea of your concentration.
Variance.
Yeah.
And
instead of doing
kind of a local mean. So in this case, it's a cycle. So it's the variance.
Like it's really way this weekend. Yeah, but it'll still be this weekend as well.
So how energetic, how big is that uncertainty?
Yeah. Okay.
And with this dynamical system, we show that we are better than actually.
I just to like a Italian restaurant that I really want to try because
So we are calling your Stokes plot.
yeah, we
and they're really good
And then
carbonara.
say now your Stokes course. That is basically with the same sampling time as this guy. And we see that with this model, we destroy. And mass is not too complex because I'm just following density. And I'm not even computing the U. I'm just saying U is a superposition of
Ready to like sit and squat out for a bit. That's yeah. I guess then why would you? That's
and
fair
then I
enough.
say, okay, let's take the first L 5 minutes. Then the token is equal to
It is just an assumption.
it's an assumption. To make that case.
Okay.
Well, I know that the Chicago Hot is weird stuff on it, so.
So again, just English on forward and backward. What is forward? I have a cloud of points at some time. Where does that cloud go, right? That's the forward. What is backward? So let's think in terms of money, right? Somebody tells you that there is some payout for you. If I end up at this value of x, this is the amount of money that I get. Okay? That's where it comes from. I'm not being materialistic here. Right, this is your payout. So you're saying, if I end up at x, this is the amount of money that I get. But now I am, say, a few days from x. I have a particular. I'm at a particular value of x a few days from this payout time. The simple question is, how much can I expect to get paid given I'm here and there's this much time left? That is exactly what this is describing. Okay, but there is a nice, again, and that makes a lot of sense if you're doing inverse problems, control, etc. It feels like you're going backwards. But again, because we are in the linear sense, the same object can be moved forward. Okay, so bear with me for one. So I will just call it the forward interpretation. It's very simple, but it'll be very powerful. Okay, so forward interpretation of backward Kolmogorov. And the trick is very simple, and it's only possible because of the linearity. So what is the forward Kolmogorov? We have du by dt plus lu equal to 0, and you have u of x comma t in g of x. Okay, this is what we've been talking about for the past 10 minutes. It seems like a backward problem. But now I want to define tau. I want to define tau as t minus t. So it's like now, it's like going backwards. And I want to define a new variable v of x comma tau as u of x comma t minus capital T minus small t. This is also a definition. Defining a tau, and I'm defining a v. And again, you know how to substitute one variable into the equation, right, and manipulate. What you would get is the following. You'll get dv over d tau equal to L and v of x comma 0 equal to g of x. As a scientist, this is more exciting to me. Or at least this, yeah, both are exciting. I said some things are more exciting and more important than others. So this is more exciting because this is like our standard way in which we think about problems, right? I have some function at time t equals 0. Tell me how that function would look like. Tell me how the expectation of that function would look like. Okay, so if you solve this, so basically v of x comma tau basically represents expectation of g of x comma tau given x equal to x naught. Okay, that's what it means. This is still the backward Kolmogorov, but changed signs. And again, you can immediately see why this is interesting, why this is useful. I mean, I told you why that is useful. But this is also extremely useful because, and this is typical, right? So if you're trying to solve some kind of a scientific problem, you know the initial conditions, or at least you know something about the initial conditions. And then you're saying, tell me how the mean of this moves forward. And you don't have to think of it as just as the mean. If you say, we say g of x equal to x, it's the solution itself. If we say g of x equal to x squared, then from that you get, it's the second moment that is moving. So you can get all of the moments. Does this make sense? So again, this is still the backward Kolmogorov, right? Remember, we are not propagating densities here. We are just propagating functions of the state. But you can view this forward or backward. And this is what I showed you in the last lecture, but I deliberately sped through it. And I don't know, some of you noticed it or not. But what I showed you is the same thing, right? So I have this scalar ordinary differential equation. And this is my initial condition. This is my different diffusion. And I showed you that the densities move like this. But let's say I'm only interested in how the mean moves forward. Okay? Initially the mean is 1 because it's a delta function at 1. And then if you solve the backward Kolmogorov or the forward version of the backward Kolmogorov, then yeah, you basically get this. Okay. And that is also what is shown here. And the same figure can be viewed forward or backward. So what is happening here? So think of the forward interpretation. G of x equal to x. So this is time, this is x. And that's why G of x equal to x means it's basically a 45-degree straight line, right? So what you're saying is, if this was my initial condition, how does the expectation evolve in time? If this was my initial condition, how does my expectation evolve in time? That is what the formulation of the backward Kolmogorov is like. But you can also flip it. If you can look at it in this money sense, okay? If you hadn't told that in my room, I wouldn't be giving you this example. That's helpful. So you're saying, okay, now flip this. Say 10 days from now, or from the 10th day, if I land here, I get this much money. If I land here, I get this much money. If I land here, I get this much money. But you're at day 4, and you're here. And that value tells you how much you can expect to get paid in how many ever days the final thing is. So, but it's the same thing that is interpreted for forward and backward, but same thing interpreted differently. But the important thing is it operates on functions and your evolving expectations. Whereas in the Fokker Planck, Perron-Frobenius, you are pushing forward PDEs. All right. Any questions here? So now that we've seen these 4 things, yeah, things can get pretty interesting here. Let me see if yeah, so this is something I just generated this morning. So now, well, we've kind of seen this before, so I don't need to show this. Yeah, what I want to show you is then now the connections between all of them. Now we've defined all of those objects fundamentally in terms of the flow map. Right, so now everything here is compact. Fokker Planck moves density forward. Backward Kolmogorov, basically the expected observable is being propagated. This is connected to the Perron-Frobenius operator, which operates on densities, and this is connected to the Koopman operator, which operates on observable. And we already saw the Koopman operator in the Liouville case, but now the question of what is an adjoint of an operator? Okay, the adjoint of an operator is effectively describing the same dynamics or physics or mathematics, whatever you want to call it, but it operates on a different object. Okay, so here is the most important thing that connects these 2 things. You can show just by integration by parts that, well, this is easier to understand. Okay, what does this represent? I have some initial density. I propagate the density forward. I basically have the density at some final time. And then I'm evaluating g of x. Okay, this is expected value of an observable, right? So remember, g of x is an observable function of the state, and this is basically the probability at some time t. So this is basically the expectation, right? Expectation of x is just x p of x, right? That's what. So this is the probability density, and this is the function. So this is expectation. So this is very simple to understand. This is the expected value of this observable at some time. Okay, this is the left-hand side. The right-hand side is a little more interesting. So we are still at the initial condition, and now we are like pulling back the observed function. Okay, so it sounds a little sophisticated, but if you apply it to the very simple, if you apply it to any of those stochastic ODEs that we've been looking at, the Markov ones, then you'll just see this is really integration by parts. That's what it is. That's what it will amount to. So this is, okay, so there are two things here. Okay, you can either write it like this, or you can write it like this. L star operates on densities. Okay. L operates on observables. And they're both equivalent. And L and L star are adjoint to each other because they describe effectively the same phenomenon. They're not like describing like different dynamics or different phenomena. It's the same thing. Yeah.
Is this telling me that if you propagate the density in time and taking expected values is equivalent to propagating the transformation of the random variable?
Yeah, exactly. It's amazing. If you think about it, this is quite amazing because so here you're evaluating this with respect to final density, and here you're evaluating this with respect to initial density, and
so you're changing what you're propagating.
Yeah. So you can say the Koopman and Perron-Frobenius are adjoint to each other, or you can say L and L star are adjoint to each other. It's the same thing. Yeah.
In practice, this could only be true if we have our finding of sampling, no?
Well, yeah, but these are all exact.
Yeah, but like reality, like in practice.
In reality, we approximate them. Yeah.
But then it would only work if the refining of the sampling is fast enough to the adaptation of the process.
Yeah, your base. I'm telling you what these things are. You're saying how do you compute them and when you equate them.
Not even compute them because the first moment will be affected by the second or the rest of the moments.
Yeah.
So the density will. This could only hold if I sample enough fast. Because
yes,
I'm showing Gaussian at the
once
end.
you say sampling, then you mean you're
I'm measuring. But there's an observer in here.
Yeah, but no. First, wait. This is exact, right? There is no.
If I assume Gaussian.
Oh yeah. Everything is for a Gaussian.
Exactly. But
right.
the Gaussian assumes that.
Wiener.
Yeah, everything assumes that it is
It's
instantaneously.
not just Gaussian. It is also Markov.
Markov that comes from Brownian, the Brownian motion. But what I say is that then the Gaussian only holds if we sample infinitely fast.
No, there is no question of infinitely fast here, because
These are exact.
the underlying equation is Markov. For the Markov equation, this is exact.
Yeah, but we agree that Markov assumes that kind of instantaneous.
Yes, but we've assumed Markov.
Yeah, I know.
Everything that goes into Markov is the starting point, and then we move forward. Yeah. Okay. So what did I want to say here? So you can see this, and as I said, in many cases you can. So the problem here is, I mean, this is very nice, very neat, but this is not what you're saying, but one of the implications of what you're saying is to compute these things precisely, it is a challenge. I'll give you a very simple, recreating these things is the start, okay? And this is already useful because if you're able to solve the backward Kolmogorov equation, then you're directly solving for the moments. And yeah, this is the point that I wanted to mention while you were talking, which is, so remember, we did not say that we need a particular g. This is true for any g. That's the other thing. G of x could be x, g of x could be x squared, x cubed, whatever. And if you have all of those, you can approximate the PDF. Of course, they don't converge in the way we want.
I don't disagree with you, but what I say is that the Gaussian assumption is a pretty strong assumption.
No, it's not. See, everything we are doing is for the Markov diffusion process.
But the Markov diffusion process assumes Brownian motion, which is a Gaussian.
No. So you have some physics problem in mind, and you're trying to reduce that physics problem into a Markov approximation, and you're saying all of those things are strong assumptions. But the starting point here is the Markov process. Then everything is exact. How you convert the physics to math is a different problem. That's not relevant to what we're talking about. It is relevant in the bigger control volume of things. I agree with that.
In the modeling.
Yes, I agree. And this is good. We're going to have some discussions on how modeling gets done. And there we address all those things. In the spirit of pretty much everything we've done in this class so far, the starting point is very definite, no ambiguity.
I agree, it's
and
analytical.
From there, everything is precise.
I agree, it's analytical, but just to play devil's advocate.
No, but these are good questions because
string theory is analytical, for example, and mathematically it's beautiful.
Yeah.
But it doesn't match reality.
This is pretty much one of the core philosophies of this class. We want to explore both.
Exactly.
So far, we've explored the precise starting point. What can I say?
Yeah.
All right. So, again, if you look at the notes, the same thing you can extend to the vector case, right? All these ideas translate over. You can get scalar functions of vector states, but all of these translate over. So I want to see if I can take a couple of questions in the time that's left. Maybe I can tell you one thing. So one other way this directly impacts numerical modeling is the following. Okay? The fact that we've gone from nonlinear to linear gives us some pretty powerful